Morning everyone. Today I will be presenting on attribute-based encryption, a cryptographic technique that goes far beyond traditional encryption by tying access to who you are, not just what key you hold. So what exactly is attribute-based encryption? At its core, it's a public key system where encryption and decryption are controlled by attributes, things like your job role, department, or security clearance. It gives fine-grained access control, supports multiple users from a single ciphertext, and advanced variants can even hide the access policy itself from unauthorized parties. To understand why ABE matters, compare it to traditional encryption like RSA or AES. With RSA, you encrypt for one specific person. If you need five people to access a file, you encrypt it five times. With ABE, you encrypt once under a policy, say doctor and cardiology, and anyone matching that policy can decrypt. Revocation is smarter too. Instead of replacing all keys, you update attributes. It's fundamentally more scalable. EE operates four core algorithms. First, set up a trusted authority generates a master public key and a master secret key. Second is keygen. The authority issues a secret key to each user based on their attributes. Third one is encrypt. The data owner encrypts a message under an access policy. And the fourth one is decrypt. A user can only decrypt if their attributes satisfy that embedded policy. Crucially, the server never sees the plain text at any point. There are two main flavors of ABE. In KPABE, key policy ABE, the access policy lives in the user's key, and ciphertexts are just labeled with attributes. And in ciphertext policy ABE, it's flipped. The policy is embedded in the ciphertext, and the user's key carries their attributes. CPABE is far more widely used because it matches real-world institutions. The data owner decides who can read their data at the time of encryption. Under the hood, ABE relies on two key mathematical tools. First, bilinear pairings functions over elliptic curve groups with a specific property E of AP, BQ equals E of P, Q to the power AB. This enables the decryption method to work out. Second, linear secret sharing schemes or LSSS, which decompose a secret into shares, one per attribute, and the secret is only reconstructible if enough attributes satisfy the policy. The field has a clear lineage. Shahai and Waters introduced the concept in 2005 with Fuzzy IBE, and Goel et al. Formally defined KPABE in 2006. Bethencourt, Shahai, and Waters proposed the first practical CPABE scheme in 2007, and in 2011 Waters published the landmark scheme with standard model security using IEEE, which remains the most cited EB construction today. EB isn't just theoretical, it's being applied today. In healthcare, patient records are encrypted under policies like doctor or specialist and same hospital, meeting HIPAA requirements. In cloud storage, files are shared without re-encryption when recipients change. Enterprises use it for document rights management and universities for restricting course content to enroll students. That said, ABB has real limitations. Pairing operations are computationally expensive, making ABE slow on IoT devices. The key escrow problem means a compromised authority exposes everything. Attribute revocation still requires re-encryption in most schemes, and critically, current ABE constructions are not quantum resistant since Shor's algorithm breaks the underlying elliptic curve assumptions. Research is actively tackling these gaps. Post-quantum ABE over lattice consumptions is a top priority. Multi-authority ABE distributes trust to remove single points of failure. Blockchain integrations can decentralize attribute management, and lightweight ABE schemes are being designed to outsource pairing computations to edge servers, making ABE viable and constrained state devices. In conclusion, ABE elegantly unifies encryption and access control. CPAB is the dominant real-world paradigm. The math is grounded in bilinear pairings and LSSS. Challenges remain around performance and quantum resistance, but ABE is already production ready for healthcare and enterprise use, and the research fountain is very much alive. Here in the last slide, I have added some of the references and thank you for your time. Thank you.